Have you ever walked into a room and instantly caught the scent of a hot, sizzling meal from 50 feet away? Or spilled a drop of nail polish remover on your hand and felt a sudden chill? Or watched a scuba diver effortlessly slice through a column of water? We go through life sorting these experiences into solids, liquids, or gases. But both ancient philosophers and modern physicists eventually realized that all of these things, the rising steam, the liquid, the diver, the air itself, are made of the exact same material. Everything you touch, from a block of wood to a grain of sand, appears solid and continuous. But at a scale smaller than we can imagine, matter is actually a granular sandbox made of individual, distinct particles. This diagram shows what happens when you drop a colored dye crystal into a glass of water. The crystal shatters into millions of microscopic pieces. These fragments settle into the tiny, empty spaces that naturally exist between water particles, eventually spreading throughout the entire volume. These invisible pieces follow three specific rules of space, motion, and attraction. These rules act as the underlying logic for every physical interaction in our surroundings. The first two rules of matter are that particles always have space between them, and they are constantly moving. They are never at rest. Because they are always in motion, particles of two different types of matter will naturally intermix. They wander into the empty spaces of the other substance on their own. Scientists call this physical intermixing diffusion. This side-by-side comparison shows the relationship between heat and motion. When you apply heat, you are adding kinetic energy to the system. The particles start vibrating, darting around and ricocheting off each other at much higher speeds. This kinetic heat engine explains our first mystery. The aroma particles of a hot, cooking meal are moving so fast they diffuse across an entire room in seconds. If that exact same food is cold, the particles lack that kinetic energy, forcing you to lean in close to smell a thing. But if all particles are constantly vibrating and darting around, why doesn't a wooden table just vibrate apart and float into the air? That brings us to the third rule: attraction. Particles exert an invisible physical pull on one another, acting like a group of people linking arms to form a human chain. In a solid state, this attraction is at its maximum force. The particles still vibrate, but they are locked firmly into a rigid, unyielding structure. They have fixed shapes and are nearly impossible to compress. In a liquid, that force of attraction thins out. It remains strong enough to keep the particles together, but weak enough that they can freely slide and tumble past one another. This allows the liquid to flow and take the shape of its container. In a gas, the attraction lines finally snap. The particles completely break their chains and move randomly at high speeds, smashing into each other and the walls of their container. Those physical impacts are what we measure as air pressure. This solves the scuba diver mystery. The human body can easily push through the weaker, intermediate bonds of liquid water, but trying to karate chop the side of the pool results in a broken bone against the maximum attraction forces of a solid. So how do you force a rigid solid to become a flowing liquid, or a liquid to scatter into a gas? It all comes down to an invisible tug-of-war between temperature and pressure. Take an ice cube melting over a flame. As you add heat, the ice warms up. But right at its melting point, 273 Kelvin, the temperature of the system stops rising entirely, even though the flame is still burning and the ice is still melting. This thermometer shows that the heat hasn't disappeared. Instead of raising the temperature, the thermal energy is now being used exclusively as a tool to break the forces of attraction between the solid particles. Physicists call this hidden energy latent heat. Pressure works from the opposite direction. If you physically squeeze gas particles close enough together, their natural forces of attraction take over again, turning the gas back into a fluid. That is how the liquefied petroleum gas in a kitchen cylinder is created. Manipulating the pressure even further allows you to bypass the liquid stage entirely. Solid carbon dioxide, or dry ice, jumps directly from a rigid solid straight into a scattered gas without ever becoming wet. Phase changes are mechanical shifts in particle spacing and attraction rather than chemical transformations. We are simply running an override on how these particles interact. Which brings us back to our final mystery. Why does a drop of liquid acetone make your skin physically cold? This diagram illustrates evaporation. A liquid doesn't require a boiling point to turn into a gas. At any given moment, a small fraction of the particles at the very surface layer manage to build up enough kinetic energy to break their bonds and float away early. To pull off this escape, those surface particles need an extra boost of power. They achieve this by stealing that required latent heat directly from their immediate surroundings. When you put acetone on your palm, the liquid instantly begins to evaporate. Those escaping surface particles absorb thermal energy right out of your skin, leaving your body physically colder than it was a second ago. Human biology relies on this physics hack to survive. When we overheat, we sweat, providing a liquid layer that steals heat from our skin as it turns to vapor. We even wear porous cotton in the summer specifically to absorb that water and expose it to the air, maximizing the surface area for evaporation. Our world isn't static. The solid table, the flowing water, the air we breathe, they are all part of a highly active, vibrating lattice. By seeing the invisible rules of space, motion, and attraction, we reveal the science powering our ordinary lives.